Assalamu alaikum, guys. In today's lecture, we will cover optical amplifier. This is actually our new topic. We have already covered optical transmitter, which is a laser, and optical receiver, which is a detector or photo detector. Now, today's topic is optical amplifier. So, what is an amplifier? So, optical amplifier means actually it amplifies optical signal or amplifies the energy of a photon. So it amplifies the incident light which comes from a laser. If I draw a schematic of optical amplifier, how it placed, for example, this is actually our laser, optical transmitter. Then in the transmitter we can have a modulator. Actually, this is a modulator. It goes to a long fiber, and because it goes through a long fiber and long distance, signals goes degraded. That's why we need an amplifier, optical amplifier. After that, it also the reason is to use an amplifier so that it can uh, goes longer further distance. So it goes again further distance, then it there is a receiver. Okay, so we are actually this is actually our today's, this is the optical amplifier here. So see, the input of the amplifier is a optical signal. The output is also a optical signal. So it's actually all optical devices. So optical amplifier is very important so that the signal can travel furthest distance before completely losing its signal, right? So this is the schematic diagram where optical amplifier is placed. Now, the basic job of an optical amplifier is the amplify light, which is actually incident light, through stimulated emission. Now, this term is very familiar to us. Stimulated emission happens in the laser. So, optical amplifier somewhat works like a laser. It's actually the same principle of a laser. It works on the same principle of a laser. So it's a laser without feedback. In a laser, this feedback happens. In optical amplifier, feedback do not happen. That's the only difference happening. So this feedback mechanism, we will discuss this term in a laser section. Hopefully our next lecture will be detail of a laser structure. You already have studied laser, the principle of operation of a laser, but how it works, the working principle, detailed principle of a semiconductor laser, we will discuss later. There we will discuss this feedback. Okay. So the optical gain realized when the amplifier is pumped either optically or electrically to achieve population inversion. Now, the question is, if it works like a laser, this must happen. Population inversion must happen. Probably you already remember because we discuss our laser topics. N2 must be greater than N1. So what is N2? In conduction band, number of electrons in the conduction band must be higher to the number of electrons in the valence band. Okay, that's is population inversion. So the optical gain means actually amplification. The amplification is realized when amplifier is pumped. Means actually extra energy must be supplied to an optical amplifier, either optically or either electrically. This is the same principle for electronics, like how our PNP transistor, when it works as a common base, common emitter, or common collector configuration, we give an input signal. For example, common, if I draw common base or common emitter or common collector system. So this is actually our input signal. Here we give, for example, here we actually have our output. So this is common emitter configuration. This side here, this side we give input, this side, and that side, from that side we got output. So whatever input we give, if we want to, for example, a small weak signal is here, then how the signal will be amplified, from where the extra energy come, because there will be VCC in the system, so that extra energy will come from the VCC, isn't it? So the signal, input signal, will amplified here by the help of VCC in electronics, right? Same thing happens. There must be a pump, extra supplying mechanism, so that the amplifier can amplify. So optical gain depends on the amplifier medium. Of course, what kind of medium means actually what kind of component you used in the optical amplifier system. Okay, so gain medium modulated as homogeneously broadened two-level system. We already know that in heterodyning and homodyne mechanism. Now the gain coefficient G is given by this equation. Okay, this equation will be more visible to us, or you can relate this equation when we will discuss about a system diagram. Probably our last lecture will be system discussion on system, how laser, amplifier, photodetector, they will be in a system, and we'll design a complete system like this one mechanism, like this schematic. Like we'll try to give a small signal, and we'll try to receive it, and we'll see what happens every steps in this system. So this equation will be more visible there. Now here uh, this small g 0 is actually peak value of the gain, and W is the incident light, means actually the input light we want to this is the frequency of the input, right? And is a W0 is the transmission frequency. Now P is the signal, or P actually PI. We can write it also P in the input signal that can be that should be amplified. Okay, and P is the gained amplified signal. PS is the amplified signal, depends on the gain medium. Okay, so this is a fundamental equation. Now this equation gives us, if we plot it, this equation will give us this gain coefficient. We'll see when we will describe a system description, that this kind of equation gives us a Lorentzian distribution. This kind of distribution we actually Lorentzian. Lorentzian. Remember this word. This word will come later when we discuss uh, system diagram. Okay, now type of amplifier. Okay, Raman amplifier. The first class is Raman amplifier. So Raman amplifier works on the principle of optical non-linearity. So far we have studied all the phenomena that optical do, they are linear mechanism. But optical also do some non-linear or non-linear phenomena arises. Raman phenomena is one of the non-linearity in optical fiber. Okay, so Raman amplifier works on the stimulated Raman scattering principle. Stimulated Raman scattering. This is a SRS is a non-linearity of an optical fiber, or in optics. So how it works? So process: atom at ground state absorb energy, goes to a higher energy. So ground state energy has to go to a higher energy, which is typically mechanism of a wait a minute, let me. Okay, from ground state, atom must go to the higher energy state, right? Okay, so it will go to the higher energy state. When the atoms falls back from exciting state, it emits the photon having different energy. with different lambda wavelength. This mechanism actually, this is saying that atom is initially in the ground state, right? This atom will go to the exciting state. In the exciting state, when it goes to the exciting state, it goes to the higher energy state or exciting state. When the atom falls back, it will fall back from that state or exciting state. It emits a photon of different energy. It now in laser, what happens? Laser, from the exciting state, atom falls completely, which do not happens for amplifier. What happened then? For example, here the first energy is E1. Okay, the when it falls back from the exciting state, the energy is E2. Where the others, so it reaches here. So we say the energy E1 and another energy is E2. What is the other's energy? Rest of the energy, which is supposed to be E3, for example. E3, that energy actually lost here. You say E1 supposed to be E2 plus E3, right? E is the from ground state to the exciting state. When exciting state the atoms falls, the whole energy will be released according to the principle of the energy conservation law, right? But when it falls, it do not falls to the ground state in the middle, somewhere in the middle. Means actually it emits a E2. What will happen? The rest of the energy E3 that has to be also released, right? And it released as a vibration in the system. This is actually non-linear phenomena. That's why we call it non-linearity. So Raman scattering is a non-linear phenomena. What happens here? This ground state, when it goes to the exciting state, it has a lambda p, which is actually pump in our cases. By using pump, we give it to extra energy to go to the exciting state. When this falls from pump, it actually releases lambda s. This lambda s actually eventually is the same as the one we want to amplify, which actually is given here. You see how it in schematic it works, Raman amplifier, right? So here you see the pump wavelength is lambda p, and the weak signal, the signal we want to amplify. For example, imagine we have a signal, but optical signal, which is a very weak signal, low energy signal. We want to increase its energy. How we can do that? That input energy signal will be inputted through here. Okay, and this is a pump energy, pump frequency wavelength, which is different than the weak signal. So pump is coming, the weak signal is also coming. This is a coupler. What will happen? This pump goes to a higher energy. The energy signal goes to higher energy, and it loses E2. If it loses E2, then it released energy in a wavelength lambda s. That energy, and this is the same lambda s, same frequency. So lambda s will be remain same, but its energy will be higher. From where it goes the extra energy? From this pump. From this pump. This one. So the same frequency, because pump releases energy in two ways, right? Pump energy. This one, pump energy. It releases energy in lambda s plus some vibration. This lambda s and our weak lambda s, these are the same frequency, same wavelength. So they combine together, and its energy goes higher, and also vibration happens in the system. Now here there is a filter. If because this lambda p, not 100% of all the lambda p will be converted to the lambda s, so that lambda p will be filtered out here. Means actually you got a amplified lambda s in the system. Okay, so SRS occurs the difference in energy level vibration, which is actually the takes place excited by one lambda and released by another lambda. This is actually uh, the main principle of the SRS, stimulated Raman scattering, where excited by lambda p, which is pump, and released by another, which is lambda lambda s. So it's lambda s. This is how a signal is amplified, okay, by this non-linearity. Okay, there are here we can see the characteristics curve of this SRS. Okay, this is amplitude versus wavelength. This is amplitude versus wavelength signal. So amplitude versus wavelength. Here, what do we do? Pump frequency? Pump is 1445 in nanometer. This lambda is in nanometer. So 1414 nanometer is the pump frequency, which is actually our lambda p pump. This one 1445. This is 1445 nanometer. Where it will be releasing its energy? It will release actually 1535. It will release energy at 1535. It will release energy of lambda p. This one is 1535. How 1445 and 1535? It depends on the choice of the material. So how it happens? It depends on the choice of material. This depends on the choice of material. This lambda s, which signal will be amplified, it depends on that one, or this one, choice of material. Because lambda p had to be go to S and release energy at lambda s. This lambda s depends on the choice of the material. So if you want to have your specific amplification of in a specific frequency, you have to choose properly your material. So you see 1545 will be the pump, and 1535, this is actually our weak signal. This is actually very weak signal. Amplitude is very low. Now this is actually the amplitude profile where this pump happens and it releases its energy at 1535. Means actually this weak energy is now amplified. See, this was lambda p, this is lambda s. This lambda s, which comes from the lambda p, is combined with this previous lambda s, which is a weak lambda s. Ultimately, its amplitude increases. The weak signal becomes stronger. Okay. Okay. So another amplifier is EDFA, erbium doped fiber amplifier. Erbium doped fiber amplifier. This is another kind of amplifier. This works somewhat same as a Raman amplification, but it different. But the concept is quite similar. So happen in heavily doped erbium ion in the fiber core. So erbium ion is erbium plus 3. That is called erbium ion. So this erbium ion is actually is in the optical fiber. So what happens is, for example, this is your optical fiber and this is your core. Okay. Now this is a coupler. So this is a core. You will couple a erbium doped fiber with normal fiber. Okay. Okay. So this is your small EDFA, small fiber. Really, imagine this is a coupler, optical coupler. Here we connect one fiber with another one. This one is heavily doped with erbium ion, with this one erbium ion. So in the core of this fiber is erbium. This is erbium ion plus 3 ion. Here this mechanism happens, and then again your once your signal is amplified, you can easily take back your signal with normal fiber core. So here is this is an EDFA, erbium doped fiber amplifier. This is amplifier, but this is in a shape of a fiber. Okay. Okay. So now, what is the mechanism? Same thing. Stimulated emission. Stimulated by this mechanism, and this happens in the C band, 1535 and 1575 nanometer. Why this C band and L band? C band and L band, because of this loss curve. Let me draw a loss curve. An optical fiber loss curve. This is a loss curve of an optical fiber. Okay. So how the loss curve happens? So this is lambda, and this is loss in dB per kilometer, for example. Now, this is a loss curve. In our loss curve, this is here happens the 1550 nanometer. Means actually 1535, 30 to 1560 is actually here, this range, or beyond 1572, which is another band, this band. You see here the loss, because we can see in the curve here the loss is the minimum. That's how we use. And also there is another reason. What is this? This peak. This is a loss due to OH, hydroxyl ion. In the fabrication, you already studied the fabrication of optical fiber. In the fabrication process, hydroxyl ion actually mixed up with silicon, which actually consume lots of energy and gives a higher attenuation. Okay, so that's why we use a C band and L band. C band, typically this is actually our telecommunication band. All our telecommunication, that's why you see up to this and beyond, this band is called telecommunication band, because here we have the lowest loss in the optical fiber, because in telecommunication optical signal has to go for a long distance. That's why uh, we use this curve. That's why C band and L band is used. Okay, so why erbium? Because erbium have quantum level that allows stimulation. Of course, because this is the stimulation emission process has to be there at 1540 nanometer. Where is the lowest possible silicon fiber? 1540 nanometer. Here the stimulation happens, which actually in this band, in our band, in this region. Okay, that's why erbium is used. Okay, now it is excited by 980 nanometer or 1480 nanometer, which have the highest loss in the silicon fiber or in silicon. Where is a 980? 980 is a much here. For example, 980 nanometer, and 1480 is actually here. 14. You see, here is loss is very high. Here is loss also high, is also very high. That will be work as a pump. There is a benefit. If loss here, when the signal will be mixed up, the fiber will be automatically attenuate them. We will see in the mechanism. Okay, for example, this is a signal which is actually imagine 1530, so 1550, imagine 1550 nanometer. Okay, nanometer signal. Now here in erbium the pump is 980 or 4. Okay, imagine this is in erbium. Here when it was coupling, there we give the pump 980 nanometer. This 980 will release or boost our 1550 signal, but when it will come out as a what? It come out like which signal will go in 1550, which is amplified, plus this 980, right? 980, because we do not use any filter here, so 980 will not be automatically discarded. But 980 will be there, but because this silicon 980 has a huge loss, so soon this signal will be die out, and when you receive in the receiver, this signal will be no more, because it's already attenuated in the. So you do not need to use any separate filter, which you had to use here, for example, in Raman filter. Okay. Okay, see what happened. So this is the energy level diagram of his EDFA, erbium doped fiber amplifier. So this is a lambda versus amplifier energy or energy diagram. What happens? There are two way of pumping. We can pump at 980 or 1480 nanometer. Imagine we only pump at 980 nanometer. So at 980 nanometer, from the ground state, it pumped to the pump band. Okay, we say it's pump band, or it is we call exciting band. So this is actually our exciting band, pump band. Now in the pump band, from the pump band, the electron, mm, uh, atom is in unstable, so it will actually fall down as a non-radio radiative decay. Okay, so or which what does it mean? It's either a thermal or vibration state, and it comes to a metastable state. It's in between. Metastable means in between state. Okay, in between state, three things will happen. Okay, uh, so you see, if this is our step one, so step two is the non ready to decay. Okay, here we are not using 1480 nanometer as a pump. We are using only 980 nanometer as a pump, for example. So there will be decay to the lower state, because this metastable is a lower state. Okay, in lower state there will be three mechanism happens. One is a spontaneous emission at 1550. Another will be stimulated emission at absorption at 1550, and stimulated emission at 1550. Same thing as laser, right? In laser, what happens? Absorption happen, spontaneous emission happen, and stimulated emission happens. Is it? Three mechanism happens. Now, if it's stimulation, then we got the laser. Same thing. This is the only signal that will be amplified. This portion will be amplified, and this portion, stimulated absorption and spontaneous emission, these two will add a noise in the system. So your goal will be, by properly choosing your material and all these things, your goal will be reduce it as much, or reduce it as much as possible, so that noise is reduced, and increase it as much as possible. Okay, so what happened? You see, 980, you choose a material such a way that at 980 pumping will give you a 1550 stimulation. Means your signal will be amplified, which actually was your weak signal. Same thing, you see, pump is 980, 980. Your signal is weak signal, which is actually 1550. It goes to optical coupler, means we combine these two signal, and you pass through EDFA. In the EDFA, this signal is already there, which is weak signal, but this signal, pump signal, this will do this processing. This one, right? It goes through this processing, and it will achieve this stimulated emission. This stimulated emission will ultimately stimulate the amplified signal in this EDFA, and that signal, which is actually 1550, will be amplified, and the excess, if there is any leakage or excess 980 signal, which is also be there 980, but because it has a very high attenuation, it will be die out soon. That's why we did not use any kind of filter in this end. We don't need it. After few meter or couple of 100 meters, this 980 signal will die out, because of this high attenuation in the system. Okay, so this is actually our uh, energy band diagram for a EDFA, erbium doped fiber amplifier. Now we will discuss about amplifier noise, because all amplifier creates noise. That's universal, because it's a mechanism. Whenever it do something, amplify something, we actually can trace back the source of our noise, which is actually spontaneous emission and stimulated absorption in EDFA. They will create a noise. Of course, they will be very minimized if you choose properly your material, but they will be there. So amplifier, what is the best amplifier? Like how we quantify amplification or performance metrics of an amplifier. So amplifier degrades SNR because of the spontaneous emission, of course, which is actually translated to the noise. All amplifier degrades SNR. What is SNR? Signal to noise ratio. Now, for example, this is an amplifier. If you input a signal, there is a noise also there. If I draw a signal, for example, this is a signal in frequency domain. In frequency domain, there will be a, if I, so this is our band of, okay, so a small noise will be there. If you amplify this, what will happen? For example, this is a 3 dB amplifier, means the signal will be doubled. If the signal got doubled, noise got doubled also. If the signal got doubled, noise also got doubled. Because how the amplifier knows which is signal, which is noise? It cannot know. It actually falls on that band. The whole spectrum of the signal will be amplified. Signal will be amplified. Uh, for amplifier, noise is also a kind of signal that will also be amplified. So what will happen if I give an input? So I had a signal to noise ratio, means there is a signal to noise power. Whenever I got output, you see signal is amplified, noise is also amplified. 3 dB, 3 dB. This is 3 dB amplified. Means the ratio, signal to noise ratio is similar, same, because they amplified in the same amount, means their ratio is similar. But because of this spontaneous emission in this amplifier, n portion got increased. Okay, so signal got 3 dB amplified, noise got 3 dB amplified, ratio was similar. But because of this spontaneous emission, extra noise is added here. Extra noise will be added here. Means signal to noise ratio will be different now. Signal to, previously signal and noise, signal plus 3 dB. Yes, this 3 dB signal, noise also was 3 dB amplification, plus excess noise, which is due to spontaneous emission will be added here. So the total noise quantity increases, means signal to noise ratio changes. Okay, so that is defined by the amplifier noise figure. We call this term noise figure. Noise figure. So noise figure is nothing but the signal to noise ratio at the input, which is input, and the signal to noise ratio at the output. Definitely, because noise increases, signal to noise ratio will decreases. Means this is a lower value, this will be a higher value always. Means noise figure will be what? Is always greater, because SNR input is always higher than the SNR out. Is signal to noise figure. Imagine in ideal cases, input and output is similar. Input and output is similar in ideal cases, when there is no extra stimulated, when no noise is added in the amplifier. But means actually ideal value is 1, otherwise it will be higher than 1 noise figure. Our aim will be to add as low as possible. So how to find this signal to noise ratio input? We know signal to noise ratio input from our previous for example, if I draw a schematic diagram. So this is a photo detector in signal to noise ratio in, so signal to noise ratio in, out. For example, this is an amplifier. So what will happen? Before we have a module, okay, long distance fiber probably, or kind of modulator, or before that is a transmitter signal. Transmitted signal. So transmitted signal is modulated, goes to long distance, lose some signal strength, and you amplify signal. So SNR in, and SNR out. What is this SNR in then? SNR is nothing but the signal to noise ratio. So this is a signal power on the photocurrent divided by sigma square. Here we are assuming that this is a shoot noise dominated system. It can be anything. Instead of lambda s, I could have writing s thermal, or s shoot noise, or s rain, or combination of all. we already discussed about the system dominated by the thermal noise, system dominated by the shoot noise, or system dominated by, we have seen it, right? So this is a noise in the so we already know this equation when there is a shoot noise. So this is the optical signal power, optical power. This is the responsivity of the detector, and P in input power. So this is signal in, input signal. Now signal output will be what? Output will be the output current. Probably it is the same one, optical power, but the noise changes here. This noise is no more same as this one. This noise will be equivalent to whatever the signal, if it's shoot noise limited, plus the noise extra added due to this noise figure, due to this spontaneous emission in the amplifier. But this is actually amplifier noise, for example. Okay. Now spontaneous emission mixed with the amplifier signal, right? That's true. So what is the spectral density of the spontaneous emission incident noise? Spontaneous emission, we try to find the spectral density is given by this equation, where this is the spontaneous noise factor, which actually spontaneous noise factor is related to what? N1 and N2. N1 is the atomic population in the ground and atomic population in the excited state. Actually, eventually, we know when the population inversion happens, N2. So this will be always higher. N2 is always higher. So N2 minus N1 is always lower than the N2. So we know then this will be always a positive value. Okay. So the noise current I. So the noise current I is always in combination of the incident optical power plus stimulated optical power, their combination. Okay. So now what happened? There is a phase difference between these two signal. Okay, let me explain. For example, you have a input amplifier. Okay, so you have an optical amplifier, you have a signal or lambda 1. This signal is amplified as a lambda 1. It has higher energy, but the same signal, lambda 1. What happens is that the phi 1, which is actually in this lambda 1, which is actually in our cases spontaneous signal ES, which is actually in the ES. So ES, we can write it ES as a amplitude of ES. So cos omega S plus phi S, some amplitude A1, for example. For our case, input signal, which is actually the input, you see the input E I N A I N cos omega I N plus phi I N. This is the input signal, input energy, or input, or the complex signal of input signal, which is actually this one, which contains lambda 1, like omega or I in, lambda in, omega in, omega is 2 pi f, which is actually lambda, and phi in, which is phi in. ES is the stimulated because of the spontaneous emission. ES is the spontaneous emission. ES is the spontaneous emission. What happens in the spontaneous emission? This spontaneous emission, see this spontaneous emission, which is actually here in SP. WS gives you lambda, same lambda. SP, where SP is equal to SN, where SN equal to SP, lambda SP. But the difficulty will be the phi. This phi, this 2 phi is not same, which is actually here. Theta. Theta is nothing but the phi in minus phi SP. lower the value, cos theta will be lower. Cos theta means cos 0, cos 0 will be 1, so the whole term will be 1 in ideal cases. So in that case we find this signal. Okay, so the you see EIN and EPS are the different frequency. Actually they are not, they will be have to be the same frequency. If they amplify signal, they're not different. It's actually wrong, they are the same frequency, but the phase will be different. Okay, so from there we can find this the spectral noise power. So this noise power is this one. This noise power is nothing but this one. This noise power is nothing but this one. See, if we know the new noise power, we know the new uh, noise signal. So we can find the SNR out. If you find the SNR out, we know the SNR in. We can easily find the noise figure. Means we can easily find, actually experimentally we can find what is the noise figure of a particular amplifier. Okay, that's all about our noise amplifier noise. I will discuss one more topic, which is actually optical modulator. That's that's one topic is can be discussed in this uh, scheme. Okay, so let me see where it is in optical modulator. Is in your somewhere in your syllabus. Let's check. Optical modulator. So our optical modulator. Where it is in your syllabus. Optical lines. Let's see. Optical modulator. Okay, is actually page 122 in our Govind Agarwal book. Okay, so let me draw what is an optical modulator. It modulates a signal, that's all, right? So how it looks like? It looks like this. Optical modulator, for example, this is an optical slab, for example. Okay, see here is the this is called MZM, Mach Zehnder modulator. This is Mach Zehnder modulator. Mach Zehnder modulator. So it's called Mach Zehnder modulator. Okay. So what happens here? For example, optical signal is coming here, P in. Okay. When the signal comes, it divides in two parts. One part goes here, and a part goes here. These are contact, but there we can apply voltage. Same thing. Here you can apply voltage. They're actually internally connected through this one. They're internally connected. This is also internally connected. Okay. And this material here, this channel in the Mach Zehnder modulator, this is called lithium niobate. Okay. It's called lithium niobate. Lithium niobate, what happened, this is actually is a sensitive by voltage. By applying, when for example the signal goes in two parts. One part goes in this direction, another part in this direction, and they combine and P out. When no voltage is applying, for example V0, no volt is 0. Here for example this is V0, no voltage is applying, P in equal to P out. P in equal to P out. Same thing. What happens if we increase the V0? If we increase the voltage here, if we increase the voltage, what will happen? That lithium niobate, this material is the refractive index changes of this lithium niobate, which is actually this one. This one, lithium niobate. The refractive index changes. Refractive index. This is voltage dependent refractive index. Okay. The refractive index changes means what? For example, I apply voltage here. I did not apply any voltage here. Here, the signal goes this direction, and the signal goes. Okay, no voltage is applied here, so signal goes as usual. The another signal, like same version of this signal, when it goes through this way, what will happen? The refractive index changes. If refractive index increases, what will happen? The speed of light decreases. Means actually, they two versions of this signal, 1 and 2, when they combine, they do not combine uh, constructively. For example, one signal arrived at this point like uninterruptedly, another signal little bit slow because you increase the refractive index, so signal becomes slow, so it will arrive this way. What will happen? There will be destructive combination, right? Amplitude, the intensity we find here changes. So based on how much, okay, you have two signal, like two versions of the same signal. This one, how much you make delay, intensity is, for example, here intensity difference on this amount and this amount at any moment. So if this is the final, if I draw, this is the final, how the intensity changes. So intensity will, okay, so if it was same, there's no voltage was applied, it was the same, what will happen? The output intensity will be higher, same as this one. Now intensity changes, not this one. So this is the intensity. You see, constructively, when this equals this, this is the intensity. The destructively, this is the intensity. So the intensity changes based on the. So what will be this voltage? This will is nothing but the radio signal. Radio. The signal you must to RF signal or RF signal. Based on this RF, the optical signal changes here at the output. Intensity changes. Okay, means actually you're modulating this optical signal based on this RF signal. That's actually the operating principle of a optical model. We actually will end here.